All right, here is our code where we have implemented our marble in a bowl. I've gone ahead and made it a sphere because there's not really a good hemisphere option in VPython, but just pretend it caps off at the midway point there. The ball's never going to go higher than that, so we don't have to worry too terribly much about that. We are setting our constants here. Just r equals 1, g equals 1 is easy to start with. I've created the marble. I've created the bowl. Right, we might put bowl in quotation marks there since it's really a sphere. And then I've given some initial conditions. Notice I am avoiding the theta equals 0 or 2 or 0 or pi, like we knew we needed to watch out for. I've set my phi value and then my initial speeds. And then here I've got my conversion because VPython works explicitly in Cartesian coordinates. So I need to take my spherical coordinates, convert those over to Cartesian. We have a negative here just so that we've got the ball explicitly going down. We just put it on there to make sure that gravity goes down and not up. And then, of course, we'll keep updating the marble's position with vector x, y, z. Here we have our loop. So here are the two differential equations we arrived at last time. Why don't we compare those over with our work here? So theta double dot needs to be sine theta cos theta phi dot squared. Sine theta cos theta phi dot squared. G over r cos theta sine phi. G over r cos theta sine phi. Then my phi double dot, let's zoom that out again. We got g over r cos phi. Let's go over here. G over r times cosine of phi minus 2 cos theta, theta dot, phi dot. 2 cos theta, and then the two dots, all divided by sine of theta, everybody divided by sine of theta. Then we do our usual Euler-Kromer update. The main difference here is that instead of updating the linear Cartesian position, we're updating the theta dot and the phi dot, then updating the theta and phi, and then we again convert those to XYZ Cartesian coordinates so that we can update the marble's position. So this is where the animation actually happens. This is the actual physics, and this is our coordinate system transformation. And yeah, I'm pretty content with this. It ends up looking pretty realistic. This is what you'd expect a marble to do. We're nearly releasing it from rest. I've only given it just a tiny angular speed for each of these angles here. So you can see it's not deviating by much with each pass over the bowl, but it does eventually, kind of trace out the space there. Let's maybe go inside the bowl. Oh, there we go. That's a cool view. So we can see it here. It is, making its way kind of back and forth across the bowl. Definitely a nice regular pattern, which you would expect, right? It's going to have a period by which it goes across, a period by which it goes left and right. And so we're just kind of seeing the interference pattern between those two periods. If we look at the bottom of the bowl, it's really interesting how it never passes through the exact bottom of the bowl, this center point here, because it's always shooting just to one side of it. Kind of a cool eyeball pattern there. So that's kind of like this forbidden region, basically, where it's going to keep overshooting that. I don't think there's a scenario in which it's gonna end up going that way, but that's kind of cool. So why don't we play around with these initial conditions some? Let's suppose we just had these angular speeds equal 0. So we were just releasing this thing from rest. What happens here is it just goes back and forth in an arc, right? Because it's got, basically it's got its angular momentum going around this way. So you can think of its angular momentum as pointing out of the screen here, or out of or into the screen here, perpendicular to the screen. And so basically it can't get past that, right? It can't do that back and forth pattern because it's got no angular momentum in the other direction. But then as soon as I introduce a little bit of one of these, let's try the theta dot, then I'll start to get the other pattern because now it's moving obliquely initially compared to how it's going to accelerate there. And you get that same kind of pattern that we had before where it's going to trace out that sunflower pattern. And then if we make this faster, it's going to move farther in each of those passes, and so you're going to see it trace out a much broader arc here. And so basically you can get the idea that by tuning the initial conditions here, I can get whatever kind of clover pattern that I want. So I guess the big question is, what do I need to do with the theta dot in order for it to just go in order for this to be as simple as possible, in order for it to close back around on itself. And so you could play around with this value of the theta dot to try to get it to, to curve back around on itself to make a nice closed loop. Oh, here we're getting kind of close. That's kind of cool. Oh, I tell you what I want to do with this. I want to put in a follow command, scene.camera.follow. This is a neat trick I learned about recently. You can have VPython follow a certain object in the window. So here we're going to follow the marble around. So this is the world as the marble sees it. What happens if I rotate while I'm doing that? Okay, it keeps that angle. It's just going to change my position. Oh, we've come kind of close to it closing back on itself. That's really close. If I go this way. See, it's deviating each time it goes around. Let's maybe take out the scene.camera.follow. The phi dot, I don't know whether that does a whole lot here. Let's try turning this to 1 now. Oh, we might have gone past I wonder if we went past the forbidden region there. That's really cool. Now we're making this little crown pattern there. Let's try turning off the theta dot and just giving it a phi dot. So now we're starting here, but we're launching it around. But yeah, that's the cool kind of patterns that it makes. It seems like these ought to be related to Lisa Zhou curves. They obviously don't look exactly like Lisa Zhou curves, but I imagine there's some kind of transformation you could do to this trajectory to see if it maps onto Lisa Zhou. So really cool stuff there with the animation. Next time we'll port this over to a Jupyter notebook so that we can take a closer look at some of the motion using some graphs.